something.
Yes, just a small one. Just
Let me
one
see.
small
Can
something.
you try now?
Yes. I think now it should be possible. Yeah.
Yes, proceed.
Okay. I think I've wanted to have us share this word from Isaiah 41. And the two verses are pertinent, and verse 10 and verse 13. And I read, "So do not fear, for I am with you. Do not be dismayed, for I am your God. I will strengthen you and help you. I will uphold you with my righteous hand." And 13, "For I am the Lord your God, who takes hold of your right hand and says to you, do not fear, I will help you." I think these verses have come to my mind at a time when those of us in Kenya, you have seen what has just been happening when the small rains began and the floodings were happening. We've seen the trips of young people who are trying to explore or just to go and be exposed to areas where they can gather knowledge. The Kenyatta University students, 11 of them were lost. Also reminded of, the kind of turbulence that some areas in this country, the Baringo to be specific, and also the parts of northern, the northeastern parts of this country. Some of those areas
Looks like we can't find our messenger today. Messenger of the word. Is he on? He may have dropped off. So boss may have dropped off at some point. But we could have, as he was sharing from Isaiah 41, verse 10 and 13. Yeah, so the context was about us not to have fear, but have faith that God is there for us amidst all the challenges that befall us in different contexts. And I think that is exactly that the message is passing to us today. Just a reminder that we shouldn't fear at all, because in times such as those, he was given context we shouldn't do so. We don't fear because we know that we have Holy Spirit who is there to guide us. I'm trying to reach to the verse itself, to encourage us and give us hope along the way. So that fear that times we do have as humans, I think from what the preacher is saying, that he will be there to give us strength, to offer help, and of course, he will uphold us in his hand of righteousness. And as such, in verse 13, we're reminded that the Lord your God is going to stand with us. We will be able to hold our right hand, and as such, we shouldn't fear. And I want to just echo those particular words of encouragement from our brother, even as we reflect on many other things. He may have given context around the country at the moment, but also this applies in other spheres of life. Yeah, think about family, think about context in terms of even our own individual battles, individual journeys that we make, academic, non-academic, family, at workplace, and the rest. So all these things are there. But should we seek the face of God, then that fear should be able to be, it should be taken away from us. And so we are encouraged this evening that in every situation, God is there to help to hold our right hand. And so that is it. I want to believe that was the message that he wanted to pass to us. Sorry, he dropped off at some point, but we can proceed. All right. Allow me that we pray then, so that we can proceed. I'm going to pray. Heavenly Father, we thank you this evening for everything you've done for us. So, Lord, we want to thank you. Even as we begin this session this evening, we want to commit ourselves unto you, that even as we reflect on the passage this evening from Isaiah 41, 10 and 13, that in every journey, different struggles that we do have face in life from time to time, we shouldn't fear because you have you right in our right with us, willing and able to help us overcome. And dear Lord, even as you reflect on this season of Easter and many other things that we are still balancing in life, we want to pray that indeed you shall help us so that we can manage the time that we have properly. We can also overcome the challenges that come our way so that in the end we come out victorious, because that's what you reminded us exactly today. Even as we anticipate a close the end of this semester, in our different programs, different courses, different units, we want to thank you in advance because you've taken us through the semester till this far. For the remaining bit of this unit, we will still want to trust for a successful ending of the semester in our different tasks that are pending. Be with us as we start our engagement this evening, because we pray all this trusting and believing in Jesus' name. Amen.
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 Great.
Amen.
Amen.
Yeah. So thank you. I think quite okay. Yes, fine. I think that was our preacher. I think he had to just drop off at some point, possibly because of the network, but we had to chip in. Yeah, so we want to thank Boaz for the encouragement, even as we begin the semester, this session this evening. I just want to bring to attention that as before we begin, I've already shared the link, or rather the link for you to upload the work that we were to do last week. So we had I assigned you some group work. So please, after the session this evening, you still have tonight, upload that work, as you can have one person uploading on behalf of the others. Because I believe with the group, one of the group members, once they submit, then automatically everyone in the group submits. So that is something I expect you to do but you can do it after today's session. So I've also shared some more tasks for us, not necessarily tasks, but some material for references for today's meeting. As I indicated, we are going to look at the last topic, as we can say so, regression analysis. But then after that, I will also have a reflection of what was pending, especially under hypothesis testing. I think we will do it perhaps next week as we wrap up. We'll have a brief session of checking on what we've done from the beginning next week, where we'll also consider a few other tasks that I may have given you along the way. So next week, we'll just do some bit of double checking on the journey that we've come from the beginning till today. So I'm going to have I'm sharing my screen in a moment so that we see where we can take a discussion today. Right. There we go. Confirm that my screen is visible. I think it is.
Yes, it is.
Correct. Now, so even before I project this chapter 9, I just wanted a reflection, perhaps a quick look back of what happened last week. We had this a brief material that I shared with you to help you to reflect on analyzing relationship between variables, and we looked at correlation, because many times as researchers we deal with variables, and so correlation become a very useful tool to enable us assess the extent to which different variables can be associated with others. And I think you can recollect the importance of this particular topic even as you think of your research ideas. Beyond that, I think somewhere in between this write-up, I mentioned that the two tools, this correlation and regression, they go together. And so as I introduce regression today, we are not going to really block the whole idea of correlation, because one often leads to the other. So I wanted you to know that we had this discussion last week. There was also a small data set that I shared with you when we were looking at correlation measures last week. I gave you a very small data set of 12 observations. And this, we were able to look at the nature of the correlation that we could estimate and measure and even interpret based on these two variables, class size and average mark. And we wanted to assess whether the two variables are related. And so indeed we did that, and we were able to offer interpretation. So having said that, then what we will do today is take it up from here and say, upon establishing correlation, is it now possible for us to link the two variables? And so the question we're answering today is one in which we want to now measure the effect. We want to measure the exact nature in terms of the link between the two variables. In correlation, that is not possible. In correlation, remember we said we're just associating the numbers in one case with the numbers in the other. So in the data set you're seeing, for example, you can see that we are correlating, or rather associating, class sizes which are larger, like those ones, and then relate with what is their average, and then compare that with the other type of, the other data set where we have class sizes which are smaller in sizes, and see their outcomes in terms of class sizes. So one can be able to just pick the characteristics, and that was correlation. So what we want to do now in the discussion for today, we want to now isolate and say, can I be able to establish a dependent variable, an independent variable? And so I link and say, is it possible to measure the effect that the independent changes in the independent variable have on the dependent? And so that is possible when we have now what we're going to talk about today, which is regression analysis. Many times when people hear regression, they often take a backseat. But when you, after the session, perhaps I hope that that will be made clearer, that it's nothing very scary. It is still manageable. What you need is just understand what happens, what we do when we have, what process goes on when you are analyzing relationships using regression models. So this session, we are going to look at the basics of regressions. And then maybe at the end of the session, I will guide that and indicate to you that there will be even different types of regression models that we can specify and estimate depending on the type of data that we do have. So having said that, I've shared this 7-page document. It's not very comprehensive discussion on regression, but I've just highlighted key issues. For more discussions of the same, please refer to the last page right down here. I've given you a few references. So if you have access to, which I think you should have access to, our library, the data library, these books are available online. And so you could be able to just look at them. So part of the material in here is also coming from the 3 books, but the last book, perhaps I've made reference to it, the book by Locke et al., that one. So I've shared with you some few pages of the book. Yeah, please note that it's available. You can download and read the chapters the way you'd want from our library. But importantly, I've just shared with you this one. So just get hold of chapter 9 and chapter 10 of the book. Just want to just a moment as I. Okay, this is chapter 8, chapter 9, sorry, on inference for regression, but this one gives you some very basic framework and understanding of regression analysis. So I would like you at some point, you can start the reading from here. It just gives you some general discussions of what regression is all about, including the nature of the questions that you can address when it comes to regression analysis. And I will encourage you to also think in terms of your areas of expertise and experience, and also areas of practice. Can you be able to develop studies or studies that can utilize this tool, because it's very, very useful. I think throughout in part of my discussion, I may have mentioned this one, what you see in that one, for example. The example on scores and other things. So those are things that you can analyze and relate in your areas of expertise, depending on what you do. So read through this particular write-up. It gives you some very basic knowledge about what it is when you're doing regression analysis. But in my discussion today, I will actually summarize what we do under regression analysis. Yeah, if I don't take you to particular sections of this book, of this chapter, I will please refer to it, because the starting point is a simply linear regression models. And then later you can even go to the multiple in chapter 10. It's about multiple regression analysis. But I will try as much as possible to simplify the content here so that you have the idea behind regression. So don't fear regression. Regression is actually very understandable. It makes a lot of sense, because many times when you're analyzing effect or impact, then this is the most relevant and the tool that can be able to answer that question. So the impact of class size on performance, the impact of teacher presence or teacher characteristics on the students' attainment levels or achievement levels, family characteristics, socioeconomic, and how that influences performance of students in school. So this is an area that I believe you should invest to understand, so that when you're contributing to debate about impact effect, then you are in the right space. So having said that, I will skip I'll leave these two chapters for you to just make reference to at some point. So maybe if you go to this one, this is the first idea. I'd like you to have a look at this concept in here. This is just a case, for instance, and I'm going to just as a way of just giving you the framework for this. That suppose you're interested in purchasing a multifunctional or a multifunction inkjet printer. How would performance factors relate to the price of the printer? So to investigate the question, I think you have a sample of 20 all-in-one printers. There's a small data set that has been shared. I think it's available in this site. And I think the data set contains information for the 20 printers with regards to those 6 or 5 characteristics. PPM implying the printing rate, that is how many pages it can print per minute. The average time, photo time, that is, I believe, for also printing the photos. The cost of the black and white ink, the cost of the color ink itself, and then the price. So you can check if this data is available here, and then you can just download, but they've just given you a sample of the same data in table 9.1. So such could be the information you need. And that is why there is a data set I've given you at the end of my summary notes that relates to something around here. That if you want to predict the price you want to spend on a certain gadget like the printer, you could use these indicators to just gauge how much one would spend in terms of the pricing. So what I'm saying in a nutshell is when you're doing regression, it is one thing to develop the technique, but it's also useful for you to know what it will be used for, even for analysis and even beyond analysis. So I want to leave the reading for you for the 2 chapters, hoping that from my 7-page presentation today, you'll be able to have, you'll be able to just face this topic without any fear. I think that is it. So I would like, at the end of it all, we'll assess ourselves in terms of understanding of the idea behind regression. Hopefully you'll find meaning in the same. You should be able to also come up with regression models of your own, thus which you can also apply in research. So many times, because of fear, sometimes we don't like numbers, sometimes you don't like models. Whenever you see models, you shy away. So some researchers tend to just be descriptive. So you don't go beyond even being more analytical, yet you have a very good topic that can be taken beyond the descriptive. So I'm encouraging you to think beyond the descriptive statistics and take things up a little bit more than that. And then at the end of it all, number 3, beyond the developing or constructing of those models, you should be able to actually estimate. By estimation, what it means is that you're going to come up with the impact measures. Those are the ones that we use that are called regression coefficients, or the numbers that will explain the relationship between the variables. Later, we will talk also about statistical inference, because you've done hypothesis testing. I will highlight to you how you will conduct hypothesis testing on the regression coefficients. And I think that will be a complete package of knowledge of introduction to regression models. So just before we proceed, the idea is we need to understand or classify our variables as being either dependent or independent. Yeah. So what it means is that you need to know what is your focus variable. The focus variable is your dependent. At times, it's called the regressand in some other technical terms. The regressand, while the independent variables are the regressors. Yeah. So in other quarters, they will tell you that the dependent variable is also called the response model, response variable, because it's the one that is responding to something, while the independent variable or variables are referred to as a stimulus. So these are the variables that will now cause the other variable to respond. And so there's quite a number of studies that you can design which will allow you to use regression analysis as part of that. So the difference from correlation, under regression, this is what you should identify, which is your dependent, which ones are your independent variables. So having said that, I must look back a little bit to the previous chapter where we spoke about correlation. And so that only tells you one part of the story of relationships. Correlation tells you about relationship. Regression tells you about relationships, but they are different. One, last week we said that when you're doing correlation, we are only associating the values in one variable to the values of the other. But when it comes to regression, then the relationship is a little bit different because we now measure the impact. We measure the average effect that the independent variable can have or will have on the dependent variable. So we want to measure the change in the dependent variable, the change in the dependent variable due to a unit change in the independent. So it means, for instance, if it's about years of experience versus wage rate. So we say that I can construct a model for wage and say the wage is dependent on maybe the years of experience and perhaps other characteristics. Let's just take that as an example. So I will now indicate an associate and say, for a unit increase in, or rather for 1 year increase in the years of experience, what does that imply for the change in the wage rate? So you can see for sure, we are concerned with the change in wage due to a unit change in the experience. And please note that we interpret them in terms of unit change. That is key, that every increase in years of education is associated with a change in the dependent variable by some margin. So that change in the wage is what I call the regression coefficient. It is the coefficient. In other words, is the impact that we are looking for. So with that in mind, you cannot answer that question without building what is called a regression model, or rather a regression equation. So it will all start there. Okay, just want to, yes, Juliet has a question or clarity to be met. Yes, Juliet, go ahead.
Okay, thank you, Daktari. If you don't mind, could you repeat
Correct.
what you have just said, that regression? I think there's a part that skipped me a bit. Thank you.
Okay, right. So let me explain it differently. Okay, many times what we are saying is that in regression, first things first, you must identify your variables. What are your variables? In particular, we need to isolate your dependent variable and then the independent variable or variables. So this will be now your focus variable. For example, in education, so if I want to understand, for example, education, let's go to wage. Let me give the example I just gave you. Wage or salaries, if you want to call it like that. We say that wage it depends on many variables. And I've just picked one, which is experience, the years of experience, so that you want to analyze the relationship between the two variables. So what it means is, in correlation will only tell you that workers who have more experience, workers who have more years of experience tend to earn more. whereas individuals and less. So the story ends when it comes to correlation there. But in regression now, we
Am I the only one who has lost Daktari?
No, you're not.
Okay.
Daktari.
Let's make progress.
Nani huyo Taslin, situfuze basi. Unaonekana unajua statistics.
Taslin siku hizi wao wanakula nini?
As it were. I do
Taslin,
not
endelea na regression.
Na wengine wako wapi? Sababu
Yes.
Sijaiongea kwa klasi ya statistics, wacha niwasalimie habari.
Watu wanakuanga humble sana kwa hii class.
excuse me. Just a minute.
Oh, sorry.
Okay. Yes, I'm not even going anywhere. That's fine. Thank you. I see you guys need some time to do some catching up a little bit, but let's just proceed. Thank you. Just a moment as I reconnect with some other network. Thank you. Hopefully you can now see my screen. Then can we proceed, Juliet? Because you are the person asking the question.
Were you really done, Daktari? Or you went
not
off?
yet. Yes, I went a little bit. We're back. I wanted to now confirm that we are back. Now, what I was saying is that for regression analysis, we now ask a deeper question and ask ourselves, for every increase in the years of experience, by 1 year, so what is it associated with in terms of a wage? So we can say that it's associated with maybe X dollars increase in wage. So which means that it will still be consistent with a positive relationship. So I'll still talk about a positive relationship, just like we get in the correlation, but the only difference now, I'll be measuring impact. It will now tell you for every change in the years of experience, I can associate that change with a certain increase in the wage. And so this X increase here becomes what is called a coefficient. The coefficient, it tells you the impact, measures the impact. So I think that was the clarification that you were seeking, so that you understand from the onset that there's something extra we are seeking when it comes to regression models.
Yes, thank you, Daktari.
Okay, perfect. Let's proceed then. Having said that, I think as we get here, I mentioned something to do with the regression model or equation. So I will be linking wage to the experience. And because we're dealing with linear models, or rather linear regression models, just like you can see from here, from the chapter I referred you to, we are dealing with linear regression models. So it means that you have a linear relationship, meaning you can now develop or come up with a linear function. So these things called regression models are basically linear functions. And so from your knowledge of math, we can specify a linear function of some sort. Typically, you expect a constant and a coefficient with experience. Just like you have y is equal to a plus bx. And so this is now a specific mathematical equation, but it is not complete. I'll clarify later why it's not a complete regression equation. This is called a mathematical equation. but it is not a regression equation because it's incomplete. So later I'll be able to mention why it's not complete, and you'll see the sense. Perfect. So this is a storyline that you need to specify a linear regression equation, which will provide the link between the dependent variable and the independent variable. From these, you get the coefficients. From the coefficients, now you can make predictions. You can now tell us that an individual earning, or rather an individual with 20 years of experience is likely to earn $50 on average. So you can now make those predictions based on the assumptions from which come from the coefficients. So in summary, we will have what is called a simple regression model and the multiple linear regression models. Those are two, but they basically meaning that from the simple case, you only have two variables, wage and experience, but then you can expand the independent variables to include more of such, and then you come up with what we call a multiple linear regression model. So rarely we apply the simple one in research. Typically, because of reasons I'm going to mention in a few. So you can look at studies that can enable you link different variables in different contexts. So I've just given you examples in here, which you can as well expand on this. For example, you're looking at the determinants of student performance. So this student performance will now be your dependent variable or your regressand, where you could have a number of regressors. In this case, you can have a list of indicators like prior education achievement, socioeconomic status, and the rest. You could also assess the teacher characteristics and the student learning outcomes. You can also measure the impact of technology integration in the institutions and how that impacts learning outcomes. So as you design your research questions, research areas, studies, then certain topics, the way they are framed, is likely to suggest that you could take your analysis beyond the descriptives to what we're doing here. So as part of your assignment, later on, or as you go along, suggest other possible study areas in education or even in other fields of expertise where you believe that you can apply this tool in research. So think about that as I'll ask that question at some point. So I know some of you are already thinking research because you're doing the research unit. Yeah, ask yourself, is the question that research question you are posing, can one be able to apply these kinds of tools in analysis? Food for thought. It's an activity for discussion. So let's now take the discussion a little bit, because I need to give you the context, the theory behind what we're doing, so that as you come up with those regression numbers, you don't just punch things in Excel or other software and come up with numbers just like that. But ideally, we will now use the knowledge of correlation and then transform that knowledge into a regression model. And so typically, if you've come across what is a regression line, it is simply like when I gave you the example of the wage and the experience, this one, wage is a function of experience. This one is called a regression line because you are linking the years of experience to wage. And so when you do maybe a graph for these two variables, using the numbers that you get for A and B, you come up with what's called a regression line. And that is something that is that's something you can demonstrate easily. So in the notes, I want you to, I think I'll need to align this properly. In the write-up that I've given you, one of the chapters, you will notice that in the textbook, on the inkjet printer example that I showed you, they've predicted the price of a printer using the print, I think this was the printing rate, the number of pages printed per minute. So you could be able to link and say, is there a relationship between the two? So I think this is something that as you read in this right up here, you'll be able to find that they've already done something around there using the data set, and they've gotten some regression numbers, which are here. So that's something you can be able to pick. So this is what's called a regression line, linking the two variables. So later, having understood the idea behind regression, you will be able to now interpret these numbers. So what is the purpose for regression? The purpose for regression analysis is to estimate the coefficients, those numbers. Beyond estimating them, you talk about them, interpreting them, and use those numbers to predict the values for price. So regression helps in prediction, making predictions. So having said that, I think I would like us to go a little bit to the idea behind regression, why we do regression models, and the idea behind, or the difference between a mathematical equation or a mathematical model and a regression model. So if you see the equation that you see right here, I would like you to take y to be the weight, x to be the experience. And so there's this small animal that we introduce. For those of us who have been exposed to research, what is that character called? For those of us who have done some bit of math before, this addition is called what? What is the name given to it? So I can now add it here.
Summation.
Summation sign. Okay. Another comment. Jamie?
Noise.
Noise. Okay. Amis.
I think it's error. I don't know.
Some error. Okay.
Some error.
All right. I see. And then the last contributor. I think I've had a summation sign. I've had a noise. I've had an error term and the like. So sure. Okay. So this is when you see most textbooks having this that epsilon symbol there. Yeah, I think, thank you. We are muted. Thank you. So we have this last character, which of course it looks like a summation sign. I think that someone saw that. Yeah, but technically we call it an epsilon. Or sometimes you find some other textbooks having U there. So rightly put, it is it's called an error term. As someone says, sometimes even the word noise is also used. Sometimes it's called a disturbance term. I would like you to see why we have this. So when you specify like this is called a regression model. Without the error term, it's a mathematical model. So this is what we can do together. I think if you go to your data set, I want us to, let me just take you back to the data set we used last time on correlation. I think if you can remember, this is the data set we used last time on the class size against the mark, which is in the part of the notes. Just to show you the idea of correlation and regression and why we do that. You can do your scatter plot from here if you want. You can insert a scatter plot diagram. Yeah, even from basic Excel, you can choose this one to see whether it's gonna, yeah, that's okay. There we go. So when you do a scatter plot diagram, those are the 12 data points that you see from the from this. So, but a scatter plot diagram gives you an idea of the relationships. But what we do in regression, we want to now fit a regression line. The regression line is one in which you're measuring the average nature of relationship, whereby the line which we are going to include in here will be a linear. It will be linear because you're dealing with linear relationship, whereby majority, or rather nearly all the variables will be centered around it. In other words, the regression line will be fit in a manner in which let's say half of the variables will be below it, half of them will be above it, or most of the variables will fall on that line. So that is the idea behind a regression model. So if you see this particular graph that I've just generated from Excel straight on from there, and check what we have in the write-up, which is, I think there's a graph right in here. So this is generated in Stata, which I think you can all do that very quickly. But the line that is now drawn right across there is called an average effect line, which is our regression line. It tells you that we are fitting a line so that the variables and the data points are either along the line or at equal distances from the line. So when it comes to the idea behind regression is that you are now saying, what is the distance of each of these these data points from the line itself? So let me just sketch and show from, for example, the first data point is point A there. So that gap there is a vertical distance, and it's what is called an error. That is error 1. I move to the small one down here, it's an error 2. This other one up here is your error 3. So each of them is associated with errors. And so because they have 12 data points, there will be 12 errors. The one that is on the line there, you can for sure say that this error, if it's 7th one, is 0 because it lies on the line. These other ones are also the vertical distances from below. So you can say from number 10, 11, and 12, because they are below the line, they give me negative deviations. The points are below the line, whereas the others, the 9 or the 8 are positive ones. So this error term is the measure of these distances from the average line. And when we are doing regression analysis, we are fitting a line such as this, which will now give you the average effects. That's why when you look at the definition of regression, we are measuring the average impact, average effect of experience on wage. So that average is one in which it fits in such a manner that these distances below and above will cancel out each other, because you can see the other ones are negative and there are only 3, but you can see the size of the magnitudes, the size of the deviations are very big. But these other ones, although there are many, their deviations are small, very small, so that you will have equal deviations above and equal distances or deviations below. So whenever you see the error term, it is because of those deviations, because we know that in life, or rather in relationships, there is never an exact relationship. You can never have an exact relationship of any 2 items. If there is any perfect relationship, then what you will expect is something like this. So I would expect perhaps this is experience, years of experience against wage. If I expected a perfect relationship, then there will be a straight line which is upward sloping like that, because we know that the 2 are positively related. Higher experience leads to higher wages. So I expect an upward relationship. So for a perfect case, the expectations are that we have every point on the line. So you'll have such situations. The 12 of them will fall on the line. But because in reality, relationships are never perfect. So you would want to now model and include the error term in each of them. And so those errors are what you see right here. And this now reflects the reality. So I just wanted you to understand the idea behind a regression model and then understand that we must include these errors to account for many other things. For example, as I said, we can never have perfect relationships. Number two, sometimes when you collect data on wage and experience, you can make mistakes. Maybe you collect data from skewed populations. So there's an error of measurement. Or sometimes instead of wage, you may not know exactly what is wage. You have individuals on salaries. There are those ones on maybe weekly wages. So there's a measurement error on some of the variables. Then this is now a justification for an inclusion of an error term in every regression model. And so as I give you the theory behind regression, it is because of the assumptions you place on the errors, then you can now estimate the A1 and A0. So if you look at this, if at some point you get to read through regression models, the basics of the why we do this is because of the characteristics of the errors that we are analyzing, and they will help us to understand, or rather to get the estimates for A0 and A1. So that is something that can happen. So all the numbers you see here, they assume certain, they make certain assumptions about those errors. And if you can see one of the assumptions from the one I've just given you from by looking at it, one of the assumptions that you make about the errors, as you can see from this graph here, is that the vertical distances of the observations below the line cancel out with the other ones above. So all the negatives and the positive numbers cancel out, so that when I now say I want to sum the errors, when I now sum them, when I do the totals of the 12, it will give me 0. Because you're adding positive and negative numbers, they will cancel out. So even if you square them, because in the theory of regression is you square those errors so that you take out this one. Those square deviations sometimes, no, sorry, it's not 0. Sorry. When you square those deviations, there will now be some very large positive number, because when you square negative numbers, they become positive. So you get a very positive number. So which now what you do is that we get the least or minimize. In the technique of regression analysis is that because you don't want a situation where the sum is 0, we often square those errors, get a positive number, and then you say that you are fitting a line, knowing that you want to get the least positive number from the errors. So that is something that is optional for you to go and read through why we do regression, how regression analysis is done. So I think I think I've not skipped anything at this stage. So like I said in here, the error term plays a very important role in regression analysis, and there are usually assumptions around it. I encourage you to refer to this to just have an idea of what it is. And so part of your task, of course, is to get to understand what are these assumptions? What are the assumptions? I've already given you one. The summation of those errors is equals to 0, or rather the mean is equals to 0. So when the sum is 0, of course, the average is 0. That's one of the things that we look at when it comes to regression analysis. Good. So this is activity number 1 for you, and number 2, sorry, in this assignment. The first one was about you looking at possible areas of research where regression is alive. Number 2, I want you to do some small research on this idea of error term. Ask yourself, why should we put it in the first place? And I've given you an example. I've given you examples of why we should include. And then number 2, there are certain assumptions that these errors are based on, just to give you the theory behind the same. So just to get, let me just go to Stata a little bit. You don't have to go to Stata. Let me just demonstrate something very quickly using this data set. But in case your Stata is on, you can do that. I'm just copying the data set again. These 12 observations, the way they are, please I've renamed this in as C size and mark, just to have one word, short word. So if I go to Stata, which I believe most of you do have. So if I want to paste that data set into Stata. Of course, I go to the editor. I hope you've spent some time to look at Stata as a tool. I'm pasting that data set in here by treating the first row as variable names. So these are the 12 observations that you do have. So with that, you can go to graph. I want you to do a scatter plot diagram. Okay, so you can go to graphs, two-way. So you can do a two-way graph scatter plot diagram. So there we go. So I've clicked on the graphical features. It will give me the dialog box for creating the graph. So first things first, I must create it. We have done this, so I'm not you've done this before. So I click on create. It will open up the options for the graphs that you want, and I want to leave it as a scatter plot diagram. So for the dependent variable, we do the marks, the class mark. Independent variable is the class size, because we are saying, does class size affect the mark? So I can just say accept, okay. So you have the graph that you have in the lecture notes, which is generated as such. So this is what you have in the notes, sorry. Yeah, only that it doesn't have the regression line. It doesn't have the regression line. So you can then, of course, if you want to fit the regression line, you can include the line. Remember, in Stata, this is the command. If I activate it, if I click on here once, you can see the command there is two-way. Open brackets, scatter plot diagram, or scatter the dependent variable followed by the independent variable. Just demonstrating this for the sake of demonstration. So if I want to now show the regression line, you can extend this command, okay, by just you just copy this this command in brackets. Sorry, let me just do it again. I want to just copy the section of the command in brackets. So I have two-way, scatter, mark, and size, close brackets. And then I change the scatter to a linear fit, L fit. I think that should work. So it's the same command. It will do the scatter plot diagram. After it has done that, it will also do a linear fit. It will fit a line on the particular scatter plot diagram. So when you do that, then it will show what we have done in the class notes. So it will now impose or superimpose a regression line. So this is called the regression line. The regression line is what we are seeking to understand in this topic. And the characteristics of the regression line are the coefficients of the model that you are fitting in. I think that is something you can take it up at some point. So for those who want to get the code again, you can just pick it up from there. So there are many things that you can do with this software if you want. But of course, Excel is also available, and feel free. Now, having said that, let's then take the discussion further before we come back to actual estimation. So remember, at the end of this session, I've given you some questions that are at the back, which I expect you to now go through. Yes, Amisi again.
Okay. Yes. Thank you. Thank you, Dr. I just have a question.
Yes.
I'm looking at the slopes of the regression line.
Yes.
What determines whether it will have, I mean, the type of slope? I don't want to go into details of whether it's negative or positive gradient.
All right. The one that you see here, or let's just go with the one that is cleaner here. One in data itself. So what do we see? Actually, I should have mentioned this before. Thank you for your question. It's one thing to get the graphs. It is the other thing to talk about it. And I think to me, getting the graphs from softwares, from computation is not a problem. But then what can you say about this? That is the key thing. So what this tells you is that without this red line, which is defining what you call the slope or the gradient, if you look at the pattern that is forming, as let me go with the first one, without the line. So this is a scatter plot diagram of the two variables. It tells you a story that class sizes or smaller class sizes, those ones around below 20, class sizes below 20 tend to score higher average because the average is over 80. Whereas classes sizes of almost in the middle range is a mixture. But comparing the small class sizes and the larger class size, the ones closer to 80, the average mark is a little bit lower. So what that tells you is that in the scatter plot diagram, it appears that there's a negative correlation between the two. So, but for you to confirm the actual nature, that's now why we did the two. It now, the regression line confirms and actually gives some bit of, with certainty on that particular observation that you made with the naked eye. So then the gradient, as you have rightly put, will be now measured by the coefficient that we will measure. If you want to get the true value, you look at the coefficient on the independent variable. So first things first here, as you do the graph, you will only know that there's a negative relationship. Or rather, if because you're doing correlate regression, it will tell you that class sizes affect marks or class marks negatively because it's a negative regression line. I think that was your question. But now beyond that question, beyond answering it that way, then our regression model will now be class mark. If you're to do a model there, class mark for a particular class will now have A0 plus A1 size of that particular class plus an error term. So this is what we call the regression model. But then when we have done that regression line you saw, then I come up with what is called now a regression line. Now the regression line will have the mark I is equals to A0 plus A1 size I. But then this time round, because we have estimated, so this is the regression line, there's a different representation. Now we have some cuts associated with the coefficients. So there's a difference between the regression model, which includes the error term, and the regression line. The regression line does not include the error term because it now gives you the linear relationship. So this is now the regression line, which you saw is a negative negatively sloped regression line. Sometimes it's also called the fitted line. So it's the same thing, fitted model. So what that you've seen there is this negative value. From the graph I saw, because it was sloping downwards from top left to bottom right, it means that the value for A1 is a negative number. The value for A0 seems to me that it's a positive number, because I will see from the graph that the A0, if I was to extend it, it will cross this line around 85. So if you're to force this line to go up to the intercept for Y, this, where it crosses the line, that will give you my A0. But then the slope now will be the gradient of the line. So that is why now the errors are not there, because this red line is now what you see here. So what we do now in regression analysis, we now estimate. We estimate A0 and A1. But then you use a technique, which I'm going to just demonstrate in a short while. So I was clarifying why we do regression analysis. So please know that when you do multiple linear regression, the story is the same. So I'm doing perfectly the one for simple linear, but then the one for the multiple, it will be the same concept. I think that is what you needed to pick from the discussion for this particular section. So having said that, in the next section, this one for the method of estimating, how do we get the numbers for A1 and A0? We use a technique referred to as ordinary least squares. Ordinary least squares approach. I'll just describe it in words, what that does. So what it means basically is we want to look at the, where's the scatter plot diagram again? It's called ordinary least squares. So you can see the word squares there. So it comes from here. We look at the errors, we square them, and then you minimize those errors. When you minimize the errors, it means that the regression line will be closer as much as possible to the data points. So this line cannot be something like that, because it's not a minimum squared errors. The regression line is fit in such a manner that those deviations, when you square them, will be the least it will be the least from the possible minimizations that you can ever get. So, I thought that would be the best way to look at it. How it works, you always do your correlation from, yes, please.
Daktari, I wanted to find out, please. Yes.
Okay, Othello, yes.
I wanted to find out on what basis is this line slanting? What is determining the slanting of the line? Is it the highest number out there? And then we see that one part of the line is falling on top of this plot, one of the scatter plots down there. Can you explain that, please?
Are you talking about here?
Yes.
Well, okay, now
it's slanting all the way up to around 80 there, something.
Now, I think that is exactly what I was trying to explain, that what determines how this line behaves is the technique that I was explaining to you, that it will position the line in such a manner that this line represents the least possible number you get by squaring those errors. I think if you are here before, we said that the dots you see there are the 12 dots, the 12 combinations of the two variables, right? The marks and the class sizes. There are 12 of them. And you can see they are scattered all over. But then in regression analysis, we want to now get an average position. So you can come up with as many possible regression lines. But this technique positions it in such a manner that the gap of every point, the gap from the fitted line, those much as they're negatives and positives, their summation, when you sum all the gaps, when you square them, because you cannot, if you sum without squaring it, you get zeros, because some of them are negative, others are positive. But the sum of those squares will give you the least value possible. And that is now how you see the values, or rather the line will position itself as such. It is not this is just by coincidence that the line fell on this data point. But otherwise it could have fallen on any other position. You may even find that in some other regression lines, it doesn't even touch one of the observations, but that gives you the average position. You're positioning the regression line so that you have those deviations being the squares of those deviations are the minimum as much as possible. The sum of those squares are as minimum as possible. So that is the criteria. We may not explain it mechanically because of I know it can be a bit laborious trying to demonstrate that. But luckily enough, we have statistical tools and formulas that can help you to just quickly develop those numbers straight. So that is the idea behind those, where those positioning, the positioning of the regression line is. So I think I was explaining how this process happens. It happens through what I've just seen from the regression line and the scatter plot diagram that you see right in here. So, but there's some mathematical procedure that involves, but we shall not cover that. It's not a part of the scope that we want to do, but it's an optional process. Some textbooks will explain, will give you those derivations, but we don't want to involve you with a lot of numbers to derive. But the techniques uses the correlation, the covariances between the two variables. Last week, if I remember, if you look at the last week's discussion on correlation, sorry to take you back again, because I told you correlation and regressions are very similar. So if you look at these two, the idea of correlation we covered last week, I just want to take you to the example we did together. This one that we had a formula which talks about the Pearson correlation coefficients. So the upper part is the covariance between the two. And the other ones are the variances or standard deviations of the two variables, X and Y. So I took you through what we mean by covariance between the two variables. And I remember explaining how you can get the same from this data set. So please refer to the material we did last week on how to compute the correlation between the two variables, the class size and the average mark. And I took you through each and every of these columns. So in regression, the same ordinary least squares method uses similar principles. So using similar principles, there's also a formula that will result similar to this one that you can compute those regression coefficients. So that's why I'm saying we will leave that as an optional material for you to consider. But it's well described in many textbooks. I'd like you to refer to this textbook for a better exposition if you want to get those numbers. But should you be interested in the same, I can provide for you the mathematics behind getting A0 and A1. Only that perhaps for you at this stage, we may not want to go into the details. We leave that on for a deep econometrics class. Now, so this, when you see this from the most popular textbooks, this is what happens. The value for the A1 or the coefficient arises from analyzing the covariance, the ratio of the covariance between X and Y over the variance of X. So it's the value A0 is derived from the ratio of the covariance between the two variables over the variance of the independent variable. So if you want to expand this a little bit, it will be similar to what we did last week. The upper part is the covariance, and it's very simple. All you want is the means and then the deviations. You multiply the deviations and get the summation. The variance of X is simply the gap between the mean, the actual X values and the mean squared, and that's it. So that will give you the value for A1. So in regression analysis, we begin from the value for A1. And then you use the value for A1 to get the value for A0. So by simply considering the mean of the variables, mean of Y minus the coefficient you've gotten in the first computation multiplied by the mean of this independent variable. So this is called the least squares formula, OLS formula that you can now use when you have a two variable model. So for us to get the coefficients for class size, or rather, class size, which is A1, I now use this formula to get those numbers. I think this is something that I can ask you to go through because we have gone through a similar one last week. So first things first, I think let me just highlight that I'm not going to work with you in this case because it's very straightforward. It's similar to what we did last week. Should you get stuck, please refer to the material under correlation because it tells you the same idea. So we had done this last week though, but I'd like you to, let me just demonstrate the process of getting there. So first things first, you have your data set. Let me just reduce the font size so that you can see the entire picture. So I know we will not be doing this in research, but remember what I told you last time, it is good to understand the procedure so that when someone is explaining coefficients, you at least have knowledge of where it is coming from. So first things first, we have the two observations, so the two variables. One of the things you will need are the means, the average for X, the average for Y, which you can simply get. And from here, we had gotten last week, it's 40 and 65. So we will need those ones in the computation for the coefficient for A0, the intercept term. So the coefficient for A1 is simply the ratio of the covariance between X and Y divided by the variance of X. And so the covariance is what we had done last week. First, that means I'll get deviations. I'll now say each observation subtract the mean. So that is column 3 and column 4. I do for the independent variable, every observation 80 minus 40, 12 minus 40, 18 minus 40. Those deviations gives us this column 3. I go to the Y variable, I subtract 65 for each of them. 40 minus 65. Please note, it's not 65 minus 40. It is the observation minus the mean. I get the fourth column. Then from there, I simply get the variance for X by squaring these ones. If I square these ones, I get the denominator, which is the variance of X. And then for the covariance is simply column 3 times column 4. Column 3 times column 4 gives me this one. So at the end of it all, I'll just need to divide this number by this number. That will give me the A1. So you can see it's a simple process if you are to do it mechanically. But as I've said for you, you cannot do this in research. But at least for statistics lessons, you should be able to understand how this is happening. So I've demonstrated the process for you in the write-up, and you can easily follow through to the extent that you can now get these numbers in here. So first things first, we got the value for A1 to be negative 0.49. And I think you can see where that one comes from. Simply this divided by this, you get 0.49. I think that one is okay. Then for the other one, for the mean, for the A0, I simply need to get the average for Y minus what I gotten for A1, and then the mean for X. So I will simply need now to use the 40 and the 65 together with the 0.49 in here. It's as simple as that. And then you have your numbers as 84. So I've done for A for you right in here, 65 minus 0.49 times the mean for X, and you get 84. So in a nutshell, the way you get those regression numbers is as such. So having done that, you now specify what is called the regression line. The purpose for doing regression models is to get a regression line. What is a regression line? a regression line is one in which you now rewrite the equation. We rewrite the equation as this. By now, in plugging in the numbers. So instead of now writing my A0, I write my 84. Instead of writing my A1, I now have the coefficient, which is a negative number, negative 0.8, 0.49. So beyond now here, it is now you to talk about the results. What does that tell you? Can I assume that using the knowledge we did last week, we can simply compute? We can compute easily. Can I assume so? I think that is a good assumption. How to calculate this mechanically, because my objective is to help you also do the same using software, because most of the times you have a very huge data set, including some of you can collect up to 500 observations. So mechanically computing those ones will not be very useful. You need software. Before I answer a question on the chat, I'd like to ask that is the procedure clear? Is the procedure clear? Sam? Okay, Anne?
We are getting there.
Paul, thank you for speaking for everyone. We're getting there. Juliet, are we together?
Yes, Daktari.
Are we okay? We can proceed. Doliana? Gaki?
We are following Daktari.
Following?
I'm also trying
Good.
to understand as well.
Yeah, it's I know for anyone doing this for the first time, never get worried. You know, this is a process. Learning is a process, it's a skill. Whenever you have an opportunity for us to break down the concepts and the idea, that's why we are here. And regression analysis is alive in research. It's so much alive in research. So even if you go to look for, if you go to look for studies which have applied regression models in education, a lot of them, I think I'll share some maybe later on, so that I'd like you to see the value of this kind of work even in your lines of research. So I think at some point that I will do that as well, so that you don't just see this as exercises that we do in class. I'd like you to also position the same in your research. Yes. Good. So if you're doing a regression model with more variables, okay, definitely mechanically the formula will be different, but we shall not do that. Once you've gotten the idea, then it's possible then that you can just implement this in statistical software, and we're good to go. Now, come the question. What do they mean? And I think this is where, this is what matters now. Beyond getting those coefficients, what do they actually tell us? Just want to guide. First things first, in regression analysis, we are measuring impact or effect because you have separated independent and dependent variables. So here, if someone was to do a very short graph, this is your class size, and this is your mark. This regression line now can, if I was to it will look something like that. Say that if I was to force this line to cut the mark axis, that number should be 84 point something. And then this number is negative 0.5, if I round it off, that negative tells you that it's downward sloping, but I can do it mechanically and say it now tells you the change in the class size, and this is a change in the marks. It is the slope of the graph. It is now a measure of change in M over change in a class size. Sometimes people use in very basic math class, they say change in Y or change in X. It's actually the measure of the impact. It tells you 1 unit change in the class size is associated with a certain number of change in the mark. So let me now give you the actual meaning of this. So depending on the nature of the problem or the study question, sometimes this number is interpreted, sometimes it is not interpreted. So I repeat that depending on how your question is framed, the constant term there can be interpreted or it can be ignored. In our case, this example of the class size and the mark, we will ignore it. It doesn't make any sense to interpret. I will tell you why. But let me interpret the negative 0.49. It tells you that this measures now the impact or the effect of the class size on the class mark, meaning that an additional member in a class, or rather by increasing the class sizes by 1, an increase in the class size by 1, an increase in the class size by 1 is associated with a drop of average mark by 0.49. I take that again. An increase in the class size. Remember, this is X is the class size. An increase in the class size by 1 student, 1 individual, is associated with a drop in the average class mark by 0.49 points or marks. So that is now the true interpretation of the numbers. And so if this was a properly crafted model, you now take that to a policy maker. They will not want to know what you did and all this math and the things. Now they would like to know, okay, should we expand the class sizes to a certain number? Should we do this? Because your results have indicated to me that there's once we have changes in the class sizes by one unit or 1 person, then it affects my class sizes negatively. So I'll have a 0.49 drop, assuming everything else is not changing, assuming that all other factors remain the same. That's how you interpret those numbers. Okay, Frank.
Yes, good evening, Daktari.
To you.
Yes, I was asking, what if we have there a plus? How will that line look? And then the interpretation. What if we have y is equals to 84 point that one, then make it a plus?
Okay. So what that means is the interpretation will be the exact opposite. So what that means is that I will first of all have something like this. So class size, and then this is the mark. Perhaps it is going to be something like that. So that now we'll have class size or mark is equals to 84.5 plus 0.49 size. So you would have such a situation. just a minute. In fact, this is not likely even to be the case. You will have a totally different numbers. But let's assume that this is what you get. Assuming this is 84, let's just go by what you see. If this was 84 point whatever number that is, then this number will just be something like that. That line will just go up where. So I will assume that this is my 84, and then the line will just be upward sloping, which now tells you that if this is the result, it will tell you that an increase in the class size by 1 student is associated with an increase in the average mark by 0.49. So this is the kind of conclusion you can come up with. But then there's a question that someone ask you, does it make sense? So there's what is called expectations. What did you expect? So the problem, actually not the problem, normally form expectations. You expect from your results. The expectations are usually in terms of the signs. Nothing else. So in my thinking, rationally, we expect this coefficient to be negative, not positive. But should you get a positive number here, then you should be prepared to justify why a class size which is bigger is having a higher average mark, or rather leads to a higher average mark. So it's upon you now to justify and explain your results. That's why you have a section for findings and discussion. So you now discuss what happens when you have a situation like this. I think I've answered that question. Frank, is that okay? Okay, Jimmy?
Yes, it's okay.
Yeah, okay. There's another question.
Yes, Dr.
Right, proceed.
I request that we go back to where we have the regression model, where we have the equation.
Where we have the equation, is it this one?
Exactly, that one.
Yes.
We have y is equal to 84.6262 minus 0.4907x. And then previously you've actually showed us how to come up with the two constants, that is 84.6262 and 0.4097.
Yes.
I'm trying to ask myself, isn't it possible for the two values to be gotten graphically? Because from the scatter plot, okay,
yes,
and then there's a point whereby you can actually come up with the regression line.
Yes.
Once you have the regression line, I think you can determine the two values graphically by first and foremost looking at the y-intercept on the other side by extrapolating the straight line up to where we have the y-axis.
Okay.
I think that will give us the first value, that is 84.
All right, I agree with you.
Then the other value is actually the slope or the gradient of the regression line.
Okay.
Yeah.
All
so
right.
I'm actually asking whether we can use that approach.
You can do that.
Okay.
Now, I want to answer you. The idea you have is right. Actually, if one would do that, it will be okay. However, there's the other side of things. First things first, that approach will require that you might need to get estimates. You might guess. That means you extend this line a little bit, right? Let me just draw another one. If I get you right, your approach will lead us to something like this. That you have, sorry. So for your case, you will have a little bit, the idea is right, but then actualization can be a problem. So you can see our scatter plot is like that. So by extending this line that way,
yes,
I get an estimate there.
yes,
I can also extend this one to this other side. So now it means that the number that you get there can be a little bit of a rough figure.
So it's all
in a
about
way.
accuracy?
It's accuracy, that's the first point, because you are likely to interpolate or rather infer what this means.
Okay.
But that is not even the main point. The main point when it comes to regression analysis is sometimes we often do the regression line extend to the axis because in some situations, those numbers where they are crossing the lines, they may not make sense logically. For example, the one I have just given you, the 84. The 84 in our case is not logically interpretable. The reason is because when you have this 84, as you can see right here, the true interpretation of this 84 is that it gives you the average mark. The 84 measures the average mark, the average class mark, where you have 0 students. Because that is what the y-intercept is all about.
I get you.
Yeah. So sometimes it can be misleading. If you say when there are no students, the average is this one. So that's why at times you find that it might be it might be misleading to extend and even represent beyond what you can see here. So in my view, what we now do is you do the estimation, you apply the technique. But lucky enough, we are not going to do it mechanically. Let me just take you, let's go to Stata a little bit. Let me take you to Stata because we are in Stata together. The same data set is right in there, right? So all you need to do is simply, if you go to your statistics, you go to statistics right there. Yeah, come to linear models and related. From the linear models and related, come to the regression coefficient, linear regression. Click on it. So if I click on it, the dialog box appears where I'm going to input the dependent variable and the independent variable. So my dependent variable is my class mark. The independent variable is your class size. And you click back the arrow and you are set. These other things are extensions if you want to suppress. Like this one, you say you want to suppress the constant, meaning that you want to remove the constant term. So that is now a matter of preference of the person doing the work. But for me, let's just leave it there, and then I click OK. So you find that you have this is what is called the regression results. So the regression results are in Stata, they appear like this. It will now give you, I want you to focus on the coefficients. The coefficients is what you're looking for. The constant here, this is a constant term. It's 84.6 like we've just done. This other one is called the class, the coefficient 0.49, and it's a negative number. It is the coefficient on the class size. This one, the mark here is the dependent variable. So in short, when it comes to regression analysis, you look at the coefficients, you focus on the coefficients right in here. And then I've not explained other things. We can explain the other things a little bit later. So, but in terms of getting those numbers, we can simply do that. Okay, let's even take out the Stata out of the picture. You can as well go to Excel. Let's just do it as well as in Excel so that you have all tools available to you. Should you not have Stata and you want to do a very quick model, just go back to your data in Excel. As you can see right in here, you can develop the same, come up with the same answers from the Excel toolbar. I just go to, I don't know what, this is your data set. I don't know how your Excel looks like. Please hit the data icon there. from the data menu, click on the data menu. I'd like you to check whether you have the, oh, sorry, Jamie.
Yes, Dr.
Yes, is your hand up or it was
No,
the previous one?
I actually forgot to know it.
Sorry. Okay. Now, so from the tool, from the data, the drop-down menu on data, I don't know whether you guys have the data analysis toolbar there. Can you confirm that you have this one? For those of us who have, can you confirm with me that you have the data analysis tool pack right here? I hope you do.
Does it depend on the version? I can see data on Excel 2010.
Oh, it should have. Do you have this particular feature right here, first of all? I hope. If you don't have it, then you can simply add it. You can add it in any Excel.
Okay.
There's a way. Just let me just try to do that. Mine already has, because I've installed. You must install the package itself. It's called the analysis tool pack. I think it is somewhere. Go to file. When you go to file, look for options right down here. Yeah, go to more options. Just want to check whether that is the case. Yes, when you go to more, you click on options. From options, this dialog box opens up, and then you go to add-ins. When you go to add-ins, you look at the you can now see you have an analysis tool pack here. You can look for the analysis tool pack. If it's not there, I think it should be somewhere. Yeah, add-ins, Excel add-ins. From the Excel add-ins, you will have a list of add-ins. You pick the first one here, and then you say okay. So there it will run. It will just include it right there. I think that's something that you can look through. It's part of the analysis toolboxes that Excel you can install, or rather, you can actually install. So add-ins is under add-ins. I think that is fine. If you've not used this before, it will not have. But once you've installed, I think it will remain there. Well, anyway, under data analysis there, right, you can now select the analysis toolbar or toolbox in here. I click on it once. Yeah, once you are clicking it once, you have the data analysis tools. There are quite a number of them. Analysis of variance, correlation, descriptive statistics, histogram, hypothesis testing. There are quite a number of things. So you choose regression. Once you choose regression, you click OK. So from the regression, now you have the options for regression in Excel. And I think here, you now input the range for the Y variable. Yeah, you can see, just highlight that one. Once you've highlighted, you click back the arrow. So the Y variable is input. You come to the X variable. You must activate by clicking the arrow, first of all, so that this window is minimized. And then you choose the sorry, just a minute, ladies and gentlemen, I think we've confused. The Y variable is the mark. The X variable is the size. So let me adjust. So for the Y variable, I'm looking at the mark. Sorry, I'm highlighting everything up to there, and then you click back the arrow. For the X variable, you click on the arrow first, and then you select the size. You click back the arrow. So you have selected the data. So the data is there. So next thing, because my data set has labels, the size and the mark, you make sure you check these labels. It must be ticked. Then the last thing you do, you can leave the others optional or leave them open. If you want confidence interval, confidence level, you can change, but let's leave it at 95%, the default one. Output options, choose where you want the data to be. So I click on the arrow again, and then you select anywhere where you want your data to appear. Click on any arrow, any space there, it will just pick its G3, and then I click back. Then these are the other options that are available, but let's not complicate because you're just testing and learning. Once you've done that, you click OK. Click OK, then your results will show up. So there's really no reason why you shouldn't really conduct your analysis even using Excel. So you can see the results are similar to the ones in the software, the Stata software. So first things first, you have the coefficient of negative 0.49, which is right there. I have the intercept term, which is what you can also see. Then there are other things. We have a p-value for each of them. You know, we have an analysis of variance, ANOVA. This ANOVA we spoke about. I don't know that we'll speak about this next week when you do the hypothesis testing. And then there will be a few things called the R-square, adjusted R-square. They are all here. The correlation coefficient is up there. So there are other things that Excel gives you, but for sure they are the same as the ones you see in Stata. So there should not be any reason why you cannot conduct regression analysis using the tools that are available. So if you compare what you have here with what you can see in Excel, is the same thing. Only that the format is slightly different. Good. So I thought it would be good for us to talk about those numbers and how to run models such as this. Please note that, yes, Josephine, you're saying something.
Is it that I have this, is it an old model or what?
Which one now?
Because I'm trying to add in the analysis, but it is not coming.
Do you mind? Let's see. Are you able to, can you share your screen? We see whether it's something that we can help. Is it possible? Yes, okay. You're sharing your screen. All right. Go to, let's see, file. Yes, options, add-ins. Okay, go to Go. Can you click Go first? Yes, good. And then check it before you don't wait. You should select that other one. Yes, that one. Good. And then okay. Now we're good. It should now be loading. Can you click on the icon for data? Go to data first. Data. Drop down menu. Click on data. Yes, there. It should be there now. You can see it at the far end, further to the right. Yeah, correct. Let's proceed with you. Click on data analysis. Oh, first things first. Where's your data, Josephine? I'm trying to look for your data in your Excel. Can you close this window first? Close it. Look where is it. Show us the data, or is it in another Excel?
Sorry, Daktari.
Yes.
Do you pick analysis toolpack or analysis toolpack VBA?
No, analysis toolpack, the first one.
Thank you.
Yep. Okay, Josephine, are we good? Or you are looking for the data itself?
Yeah, I'm looking for the data.
Okay, look for that. Mrs. wants to say something.
I am among the people who are still struggling because we can't access data. Now I'm wondering, can I use Excel to do the same thing?
Why not? That's why we have all these things.
Okay. Thank you. Yeah. I think that now I'm sorted because I honestly cannot access data.
It's okay. So even for the project that I'm gonna give you at some point, it's like you're doing a report. You can feel free to do your reports in either Excel, if you have Stata, if you have SPSS, as long as they are able to answer the questions that we will give you for the project. It's like research. I expect perhaps you give me research outputs or results that are in the framework of either Excel, work with Stata or SPSS. I think that's fine. So I'll be flexible in ensuring that we are able to do what you can do. Okay, so good. Now let's see from Excel.
Excuse me, Daktari.
Yes, Othello.
Can we do a mock project?
Throughout what we've been doing, though, I'm yet to. I'll share this at some point. Throughout chapter 1 up to what we're doing today, we look at different things. So it's like a round down. So I'll do, when it comes to the project, for example, we now go back to chapter 1, okay, chapter 2, chapter 3. So it'll be awesome. I will give you data. Part of one, you'll have two sections. That is, I'll give you let's talk about it maybe at the end, but it has to be whole encompassing. I'll mention that as we close. Let me not disrupt the flow of the ideas for now. I'll comment later so that I leave you with all the tools to use. So there will be the part for the analysis of data. There will be a small section for also the theory a little bit, so that you have a balance of everything. Okay, I think that is fine. Now can I proceed with the rest of the discussions?
Yes.
Okay, I think good. So you're free to use this. The other thing, if you are still if you are still in the Win data, if you go back to the data drop-down menu right there, you go to the analysis toolbox right in here. I hope you can also see that there's an option for correlation. Yeah, I just want you to also check whether there is correlation somewhere. You can see right in here. So that is correlation. Then you choose correlation, you activate the features for correlation. So you now have the input range. The input range for correlation still collects, just pick the data set again. I click on it. And then you select the data. Let me see whether yes. Make sure that the correlation window is still open. I pick on this. Remember, for correlation, you do the entire. Both the variables have selected the entire data set, including the labels. Once you've picked that one, you click OK, or rather click back the arrow. So you can ignore the other ones, columns or row. I have labels there because the labels must be indicated. You can see the labels are right there. And then you choose an output cell where you want your results to be. I can activate it and then even throw it somewhere. Sorry. Once you've activated, you must select by clicking on the arrow. I want to pick any cell, like in Q, I think should be Q4. I click back. So you've selected everything you need. Then I click OK. So you can see you have your correlation coefficients. You have correlation coefficients. So you can definitely see that whatever I have here is a correlation matrix. So that is your correlation matrix. What's happening here, but it's okay. Okay, this is your correlation matrix. So which has just the way we do it in Stata, and you have this number. I hope you can see that the correlation coefficient here is the same as the one that you see here. So this is multiple correlation coefficients. When you do regression, it will also give you the correlation coefficients right here, because you can see the same thing. Just want to, for the sake of the other things you see in a regression model, I just want you to be aware that we have what is called an R-square value and then an adjusted R-square value. That is also important to just note. Those are the two numbers. They are very much related with each other. At some point, I think I've given you a task to read about R-squared and F statistic, which I think it's right here as well. Just want let me just highlight the key things I want you to take note of. When you are doing a regression model, what are the things that matter? First of all, you have the correlation metrics right there. I think the problem with Excel is not flexible enough on this one to give you maybe more options. But you see, when you did the same in Stata, you have made other functionalities or other options to choose, even significance level and the rest. But that's something for another day. But the most important thing is that you ensure that you get this right. What does that number mean? Now, I'll talk about R-squared later as we come to a close. There's also a F statistic, which is very important to interpret for us. I want to tell you other things that matter for a regression model. We have the coefficients right there. So for every coefficient, there's a standard error. For every standard error, you can generate a T statistic. And most softwares gives you the probability value. And what we did in chapter 4, I think we have the confidence interval. I think the confidence interval is this other, from 63 to 105. That was the discussion we had at the time we were discussing confidence levels, confidence interval. That 84.6 lies between a lower value of 63 and 105. Now, just want you to just have a simple calculator later on. If you divide the coefficient by the standard error, you get a T statistic. You can just do that one at some point. Yeah, once you get the recording, some of the things you can always demonstrate. The coefficient divided by the standard error gives you the T statistic. And statistical softwares also give you the p-values for the same. So this is like, please ensure that you know how to read this number here. It's written in standard form. So basically, this is 4.94 times 10 raised to negative 6. So it's a very small number. It's 0.0000494. So it's a very small number there. Then for this other one, for the coefficients, hopefully you can see that you also have this standard error. When you divide the 0.49 times divide by 0.21, you get the T statistic. And there's always an associated p-value. So each of these are important for interpretation. So we just interpreted the size of this, but these other ones also give meaning, either the standard T statistic or the p-value. They tell you about whether the effect is significant or not. So it's one thing to say that an increase in class size leads to a drop in the average mark by 0.49. But in hypothesis testing, we now say, is this drop of 0.49 statistically significant? So that question is answered by either the T statistic or the p-value, So if you want to understand that bit, because it's an hypothesis testing, remember I told you all the time, whenever you have an hypothesis testing, whenever you see a T statistic or a p-value, know that there is a null hypothesis and an alternative hypothesis. what hypothesis are you testing? Just to, as you read through, you'll notice the following. So those coefficients are assessed for significance using what's called a t-test. The t-test, when you're doing a t-test, when you're computing t-test, please refer to our discussion on standardization. Remember, when you're doing the Z scores, the T scores, what we do there was to say, when you say the Z score is equals to maybe the value minus the mean divided by standard deviation. Or when it comes to the T statistic, it's the same thing, X minus the mean divided by the standard deviation of course, or the sum. This is sample standard deviation because T is for small samples. But the idea is the same. If you remember this idea when we talk about standardization and distribution, this T statistic that I've told you comes from what you see here. So what it tells you is that I told you that T statistic is given by the coefficient divided by standard error. I want you to relate with this formula here. It tells you this. It says that the T statistic is given as the coefficient minus 0 divided by the standard error. Please note that the standard error is the same as standard deviation, just for the sake of making it clear. So what that tells you is that when you're doing the T statistic, like I told you here, when you divide 84 by 9, you get 8. And that's a T statistic. And you know how to calculate T statistic. It is the value, in our case, the coefficients, subtract the population value divided by the standard error. So this means that in each case, the null hypothesis is that the population coefficient is equals to 0. So it tells you that even though you got a coefficient of 84, this coefficient of 84 is from the sample of 12 cases. This 12. But you want to know whether this 84 is a true reflection of the population value. Remember, that's why you do sampling. You do a sample so that you can infer about the population. So we estimate this because you don't know the true value of the population constant, the true value of the population coefficient. So you now do hypothesis testing and say, there is a value that you've gotten significantly different from 0. Okay, is A1 significantly different from 0? So that is a null hypothesis. So the null hypothesis says that A1 is equals to 0, meaning it is not statistically significant. So this is now extra knowledge which you may not get from the discussions in the notes, but it might be useful for you to understand the statistical significance of those coefficients. So for each of them, the null is each of them is not significant against an alternative that the coefficient is different from 0, meaning it is significant. So when you're doing regression, you must go to the extent of assessing whether is the effect significant or not. So this T statistic is the one that helps you. So what is this is now the rule, or rather, what do you conclude? Please refer to the knowledge in hypothesis testing. Rule of thumb. The rule of thumb. As you did in this, when you're doing hypothesis testing, if the p-value is less than 5%, So I just want to provide if I'm using 95% confidence interval or 5% level of significance. So if P is less than 5%, or rather, if P is less than 0.05, then reject the null. That has always been the rule of thumb in any regression, or rather in any hypothesis testing. Whenever you have the p-value being less than that, then you reject. If you're using the p-value, the same way, if the t statistic is less than 1.96, then it's the same conclusion. So if you're using the t statistic or if you're using the p-value, then it is the same thing. Good. Now let's do the alternative. In the alternative situation, if your p-value is greater than 5%, what we're doing is that we do not reject null. In other words, we say that the coefficient is not statistically significant. So that number you gotten, for example, negative 0.49, you must subject it to hypothesis testing and assess whether is it a significant effect or not. So this is the rule of thumb, that assess using the p-value or use the t-statistic. So having said that, then let me go to the results. I hope, do I need to clarify that or is clear? Because that is a point where people often forget and they keep repeating that and asking it over and over again. So in my view, I hope that rule of thumb is clear. So having said that, I want someone to tell me whether is the effect of class size on marks significant. One person to give me the answer and the reason. Yes. Do we have a significant effect? This negative 0.49, is it significant or not? Okay, I've seen one answer. It is significant at 5%. Good, I'm seeing two responses and now third one on the voice.
From the p-value.
From the p-value, good, nice, thank you. So thank you very much, that's how you do. So for your analysis, as you do your report, when you've done your model like this, you now analyze and say, as part of the interpretation, an increase in the class size by one student is associated with a drop in the average mark by 0.49 marks. Since the associated p-value is less than 5%, I hope you can see that is 0.04. It is less than 5%. It means that this effect is statistically significant. Yes, somebody is saying something?
Excuse me, is
Secretary, can we go back to the example briefly before you come back here?
Just a minute. Let me. I heard the voice of Othello. There was another lady speaking. It was Josephine.
Yeah.
Okay, let me so that I can Josephine. Let me hear your question as well.
Okay, I saw the negative value, negative 0.49.
Yes.
But it seems that we are ignoring the negative.
No. It's okay. Let me clarify that, and then I go to Othello's question. We are not ignoring it. The negative is in the statement. If you heard what I said, if you can listen a little bit keenly, I've said this. an increase in the class size by one person is associated with a drop in the class mark by 0.49. So already I'm saying this one is increasing, the other one is dropping. So that is now the negative aspect of it. I hope it is clear, Josephine.
Now the p-value is less than 0.05.
Yes.
Being negative.
No, not being negative. Eh? First of all, I wanted us to be clear on the coefficient first before you go to the p-value.
Okay.
Yeah, I wanted to clarify the fact that here, when you had me interpreting, I did not say negative 0.49 because that negative is about the impact. So I've said an increase in the class size by one student leads to a drop in the class mark by 0.49 points.
Yeah.
So I think that is clear.
Yes.
Then I say now for this other one, for the significance aspect, we now say in the second statement, since the p-value associated with that effect is less than 0.05, then it implies that the effect is statistically significant, full stop.
You reject the hypothesis.
Yes. So you are rejecting the null hypothesis of no significance. Remember, that is where the null hypothesis. This is where now Othello wanted me to go to. So the null hypothesis is no significant, not statistically significant. So you are rejecting it. So when you're rejecting it, now you confirm that it is what? Statistically significant. Othello, what was your question?
So just then scroll again up, and then we'll see that one where you brought T into the picture. That's why, yes. No, yeah. Go up again where you brought T into the picture. That's what. No, we go again down.
Is it like this? No.
No.
This way.
Up.
This up. If I go up here, is it there?
Yes. Yeah, this is the one. Yes. We brought T into the picture. Yes.
Yes. Oh, I wanted to clarify. You wanted me to clarify that one?
Yes, please.
Okay. So here, I wanted you to have options. You only choose one way of interpretation. If you are comfortable with p-value, let it end there. So you can either interpret the first one, but if you feel that you want to speak about the t statistic, you can use that one, but then you don't have to repeat for p-value. Just choose one way of interpretation. So here, what it means is that in statistical terms, if you can recall the topic we covered under hypothesis testing, one tail, two tail, whatever, that class session, if you can remember the cutoff points, when you are at 5% level of significance, the z-score was 1.96, or the t-score is 1.96. At 1%, 2.58. At 10%, 1.64. So these are the cutoff points for the levels of significance at various levels. So because we were using 5% all through, that's why I made reference to what? 1.96. So it tells you that if it is less than that value, it means that you are going to, oh, sorry, I think this is wrong. Thank you, sir. I think I've now seen it. Just a minute. Thank you. I think this is a good question. I think I should have just. Good. It is the other way around. Thank you. I think now I think this was a good question to ask because we are clarifying things. Thank you. It is p-value greater than t greater than 1.96. I'm sorry. Sorry for the confusion, but this is the right one. So when t is greater than 1.96, you reject. If it's less than 1.96, we do not reject. Why that is the case, I hope Let me just spend a second to clarify that. If you remember what we did last time, it's either at negative 1.96 or 1.96. So please know that it's either on the on whichever side.
Yes.
Yeah. So T you can either get negative or positive. I hope you know that. But for P value, it's always positive because it's probability. So what I've said is if the P value is higher than 1.96, if it's higher than 1.96, reject. Null. If it is less than negative 1.96, this other side, you also reject. So if you struggle with the T, just draw this sketch and then label your acceptance region and label your rejection region. Because T can either be on the negative side or the positive side. So in here, if you have positive values for T, which means that this positive values is when when your coefficient is positive. If your coefficient is negative value like the one we have, it will be a negative number. So it will depend on whether it's less than that one, greater than that one, or within this range. So please, I just wanted to know that for T statistic like this one, the coefficient is negative, so you expect a T which is negative all the time. This one, the value here is a positive number, so the T will also be positive. So that's why I wanted you to be very cautious. For those of us relying on the T, but I always insisted you are safer with the P value. Just use the P value and you are sorted. So this will apply whether it's a regression in linear or multiple. It doesn't matter which one we are in. Good. Next thing, I may not have followed the discussion lecture notes, but I'm just giving you the overall discussions in here. There's something called the analysis of variance, ANOVA. That section there is your ANOVA. There. This is your ANOVA results, analysis of variance. Analysis of variance gives you certain indicators. It tells you certain things. The ultimate purpose for the ANOVA is this. That T statistic. Oh, no, sorry, F statistic, sorry. F statistic. And actually the statistic is that one, sorry, it's 5 points, that one. This is the P value. This gives you the P value. This gives you the F statistic. Just want to, for those of us who are interested in looking beyond the numbers, if you go to this coefficient of size, this T statistic, can someone square that number? Negative 2.29329 times or square, what do you get? What does it come? What does it become? Yes. Yeah, we are almost coming to a close.
5.259.
So you get this value for the F statistic. And you can see the P value is the same as the other one. This is only true when you have a two model, when you have only one independent variable. But when you have more, this relationship does not hold. Just wanted to give you one thing. Just I'll interpret two things and then I let you go. This F statistic, the one in Excel, the last value there is the P value. But in Stata, the numbers are here. This is the F statistic. and this is the p-value for the F statistic. They are the same. So what do they tell you? So F statistic, let me give it, first of all, F statistic or the F test. It's more usable for multiple regression, multiple linear regression model. It may not be very useful for a simple one that we did, but I want to just give you the idea. I want to say the mark. Suppose the class mark is a function of the class size and perhaps the parents, or rather, let me call it teacher quality. Okay. And then maybe score in English. Let me just give that one. Let me give 3 variables. Suppose I have a model with 4 variables: the marks, the class size, the teacher quality, and the marks scored in English, assuming that English marks can help you to explain your overall mark. So what you do is that you'll have a very big model. Let me just quickly write it. You don't have to write this. A0 plus A1 size plus A2 teacher quality plus A3 is the mark in English plus an error term. So this, you will now make more sense with an F test. What the F test tells you is it is a test for joint statistical significance of the variables. The keyword I'm underlying there is the joint. Similar concept. It means that you are testing a null hypothesis which says the independent variables are size, and the coefficient for size is A1, and the coefficient for teacher quality is A2, and the coefficient for the other one is A3, and they're all 0. This is what we call joint statistical significance. It's like the t-test. The only thing is that here we're doing the combination of all of them. You are saying all the 3 variables are not significant. So all variables, all the independent variables are not statistically significant. Against an alternative of all the 3 variables are different, and they are different from 0, which means that together the variables are statistically significant predictors of the marks. So it's called a joint statistical measure. So you are combining them together. It is like the t-test. It's an extended t-test. I hope that is clear. So when you go and do your reading, because there's a section that I've told you to go and read. Please, if you read these 2 sections here, this is for you. I've already done a little bit of the idea for you from the handout. And then I'll also ask you to look for the R-square value, what that means as well. Okay, so this is the last one I interpret, and then I ask you now to go and explore this a little bit more. So for R-squared value, this one, sometimes the most accurate one, for one variable, you can interpret the R-squared. It tells you the true, when you go and read the handout, it tells you, it now tells the question, or answers the question, what percentage of the total change in the marks is explained by changes in the class sizes? I take that again. Or rather, if you want to be qualitative, to what extent is the changes in class size causing changes in the marks? So the answer is 34%. If you're interpreting the R-squared. If you have more than one variable, like the one for the example I just gave you, you interpret the second one for called adjusted R-squared. You can now say the class size, changes in class size account for up to 34% of the changes in the class marks. So you can it makes sense because you only have one variable called class size, but it's not the only thing which affects marks. So if it means this R-squared tells you that if I add more variables, like the one I've given you here, this example here, if I had more variables, if I had a model with 3 variables, like this one, then the coefficients, this R-square is going to be higher, because you are now saying the 3 variables are explaining 50% and the like. So what is the bottom line? The bottom line is that you want our R-square value to be as high as possible. In fact, the limits are 100%. It never goes beyond 100% because it's a percentage. 34%, 38%. So to what extent are you explaining the variation in Y? Good. I think I don't know whether there is a question. Yes, Othello.
This one is about hypothesis. So on average, how many hypotheses might you be permitted to test?
In a regression model, there are quite a number. The ones we've just done today are 2. We've done t-test for the coefficients 1 by 1. You conduct a test for the coefficient, t-statistic, and then the test for the other one is this f-test. So in this case, it's only 2 that you do for now. For now, we are only doing for the 2. But in a typical model, you can even have the other things that one can do beyond what you can see. But let's not go there. Let's just talk about the 2. I want any other question as we come to a close. Maswali nyingine? Any other person with a question? I think we're good. So going forward, I would like you to do the following. Okay, Jimmy.
Okay, I thought Othello was asking.
Yes.
In a research study, how many hypotheses are we allowed to do the testing?
Okay.
Yeah.
Okay. Let me answer it. I want to see if there's a different question, then if you are doing your research, depending on your hypothesis, your objectives, depends on the objectives. What is it that you are seeking to study? If at all one of the objectives, for example, states like you want to assess or investigate, measure the effect of this on that, and your approach of analyzing it is regression, then it goes without saying that in your explanations, when you're interpreting, like what we've been doing, we've been interpreting the significance of the coefficients using the t-test. You also have an f-test to interpret. And depending on any other analysis that will follow, they can be more than 2. But if you have a different objective, which is not necessarily regression, like the session we had under hypothesis testing, you want to see whether there's a significant difference in perception between males and female, then you can propose maybe a difference in means test. So that becomes a separate thing. But in a regression alone, it's like this. You can do 2 or more, but within the same kind of objective. But if you have a specific objective targeting on testing hypotheses between groups and the like, then that's a different question again. It will be a different question. So in some cases, some researchers are, if they are more qualitative, you don't even have to do hypothesis, depending on the level of depth in your research. But for sure, at your level, please ensure that you have some hypothesis testings. Good. As we come to a close, I would like you to redo this session. On a day you are very fresh, wake up in the morning, go through the content one by one, up to what you've done. If you notice, I've actually gone through each and every section of the notes. The only thing we did not do is to estimate a bigger model. And that's what I wanted to challenge you to do this week. And then next week, we will clarify. I did t-tests. I've given you some interpretation, including the null hypothesis. I've also mentioned something about F statistic and the R squared. So yours is to go back to the last page. Please go through the revision questions in here. But I'd like you to look at number 4, attempt question 4, because next week I will talk about number 4. But please attempt it first. So this is about James, who wants to predict the price of an inkjet printer. Yeah, if you look at this data set that you have here, is the same one that you have in the textbook here, except for some variables that I've added. So this data set in table 9.1, the 20 of them, it's exactly what you have that I've shared with you in the notes for the first 2 variables, but I've added other things, my own data here. So I want you to play around with this data set and see if you can do a regression model even in Excel or otherwise. And then give it a try if you can answer the question there. So the data I've also shared in Excel, the same data set, go to the sheet under question 4. Yeah, this is the same data set, you have it. So I've arranged for you, try and see whether you can estimate a model. So that can be the challenge for the week, so that when I meet you next week, we will just do a wrap up. I want to see if there's a question that I need to clarify before we leave. We are leaving right now.
Dr.
Yes, please, Terry.
Have you been able to create for us the link to submit our group work?
For the submission, yes, it's ready. I just did that now.
Okay.
No, I did it before we started class. Yeah.
Okay.
So please know that that is available. Check ensure that your work is uploaded.
Sorry.
Yeah.
It appears that it's actually running up to end of April.
Oh, it's up to. Oh no, I thought it's tomorrow. I think I may have missed out. It's supposed to be tomorrow. Oh, sorry. Yeah, then I need to adjust. Sorry. I think that should be the one for. Thank you for notifying me. But I think I just thank you very much on that. I will do that.
So can we proceed to submit?
Please submit it. Submit.
Okay.
Yes.
Okay.
So as we go now, I'd like you to on somewhere on Friday. Oh, is someone's hand still up, Nyawita? I think, or it was.
Yes. Good evening.
Good evening to you.
I'm asking the need for submission is in which week?
It is correlation, week 9.
Week 9.
Please go to week 9
okay,
when you did correlation. Yeah,
okay.
It's important that is happening, so that by the time we meet next week, I'll return all your assessments, and then on Friday expect the final project. I'm still tying up a few confirmations, so you'll have it on Friday. Yeah, I think that is fine.
Okay, thank you.
Good. Anything else I need to know? We meet
Which Friday are you talking about?
I'll post the project for the end of term, the final project for the unit.
Okay, this Friday.
Yes, it should be ready anytime from Friday, but then that will run through for a few weeks till the end of the semester.
Okay, thank you.
Yeah, so it's not, yeah, this is the end of semester, the last day of exams, you upload, but then I'll give instructions next week. Good. Now let me allow you to leave. I wish you well for the rest of the week. Enjoy your Easter holidays. Take care, and then meet you around.
Thank you, Mwalimu.
Thank you, Mwalimu. God bless.
Blessings.
Yes,
Thank
boss.
you.
I can see you. God bless you.
Chris Wekesa, how are you? Chris?
What? Hey, hi, Sam. Hi, brother. How are you?
Very well, man. I just wanted to ask something quickly. Are we going on Easter break?
Yes, we shall.
When?
I'm sure the memo will be out by tomorrow, if I'm not wrong.
Okay.
Yeah, and the resumption should be Tuesday, because Monday will be Easter Monday.
Yeah,
Yes.
I understand that. So are we likely to have tomorrow's class?
Tomorrow's class is which class, by the way?
Profs, E25. 625, I mean.
I'm not sure. Tomorrow we're having a requiem mass for one of our students, so I don't know if
in the evening.
But of course, that will be in the evening. Probably we can. We may. I'm not sure.
Okay, all right. Good. Maybe I will have to wait for the memo.
Yeah.
Okay, thank you, bro.
Thank you. Thank you so much.
Chris.
Yes.
Hi.
Hey, Liz.
I thought Prof did a class on Monday, so tomorrow probably it could be Biblical Foundation.
Yeah, it was about actually. Yeah, you are right.
Let's wait and see.
No. That was our class on Saturday. So we will not have biblical. We'll still have Prof tomorrow.
Oh, so this week there's no Biblical Foundations?
No. Until next week now.
Oh, that bypass. Thank you, Maureen.
Now,
Welcome.
what about the journal, the weekly journal?
But
Are we
we
still going to do it?
Marlene. But we were told that we will do the class on weekend.
Which class?
We were basically exchanging the Biblical Foundation.
Okay,
weekend is a holiday, guys. And then
I know, yes, it is a holiday, but that is what was said, that we will do the class on Saturday. So maybe they weren't.
Saturday is a holy Saturday.
Remembering
Cindy, where was that said?
Where?
Yeah, where was it said?
Let me look for the message.
It's actually Ayuya who said that. He said that
Yeah, it's Dr.
he will
Ayuya who
talk
said
to. She said that she will talk to Dr. Munyao. They pick the Monday class, and then Dr. Munyao can come in during the.
Yeah,
but
it was saying
we can
it is raining.
assume that it wasn't in Ayuya's mind that this weekend would be Easter holiday.
Yes.
Yeah, because she said it's raining heavily in the place where Prof is. God willing,
Yeah,
will make up
We
tomorrow.
I understand
Then
that.
Dr. Munya
My
will come on
imagination is that
weekend.
it probably did not
Yeah.
occur to her immediately that this weekend is Easter.
Yeah, I agree.
Sure.
Yeah.
We can
But
set the
Maybe
weekend tomorrow.
we'll just have
No
to wait.
problem.
We'll just have to wait for the memo maybe tomorrow.
yeah, let's wait and see how it goes.
Yeah, good.
All right, sawa. Have a good night.
Good night, guys.
Bye.
That's an irony.
Good night.